Good morning, everyone. Today we are going to continue our talk about applications and the processing of metal alloys. So this is our first time to talk about this one. So you can see how important this topic is. And here are today's objectives. And we want to learn the heat treatment of metal alloys. This is very important in industry. And hardenability of metal alloys. And also we talk about precipitation hardening, and which is one of the most important strengthening mechanism for metal alloys. Uh, Thermal processing of metals, we talk about heat treatment as annealing. And so here is annealing. Annealing is a heat treatment in which a material is exposed to a elevated temperature for extended time period and then slowly cooled. So this is how we do annealing. And annealing is carried out to the purposes include relief stresses, because at the high temperature the residual stress can be released, and uh, increase softness, ductility, and toughness. And all the third purpose is produce a specific microstructure. Um, Annealing consists of the three stages, as the name this is describes. First, we heat the material to the desired temperature, and second, we hold or soak these metal alloys at this very elevated temperature, and then we cool it, and usually to the room temperature. So this is how we do annealing. And any questions regarding this slide? So here is this picture. This photo shows the thermal processing of metals. You can see. So here is a iron carbide we call cementite phase diagram, and in the vicinity of the eutectoid, indicating heat treating temperature ranges for plain carbon steels. We focus on plain carbon steels, which means that we do not add any alloying elements there. So here you can see this is a composition with the percent of carbon from 0 to 1.6%. And here is this is the temperature. So this is the temperature, right? So this is this is this is A1. So this is A3. So this is a full kneading. And so here is, and this is another one. So this is normalizing. These are different the areas. And so here is we talk about. Uh, so here is I'm going to show the types of annealing. And the types of annealing, as the definition describes, annealing means that we elevate the temperature to a certain desired temperature, elevate the temperature to a desired temperature, and then cool it slowly. And it can achieve the stress relief, reduce stresses and resulting from plastic deformation, non-uniform cooling, or phase transformation. And also, so this is the first first purpose. Second one is spheroid dies. Spheroid dies means that we want to generate a spheroid die, to which are the microstructure for steels. Make very soft steels for good machining. And we call this is spheroid dies, and heat just below this eutectoid the temperature and hold for 15 to 25 hours. And so next one is a full anneal, and also for steel, make a soft steels for good forming and heat to get this is gamma arsenide, and then furnace cool to obtain coarse pearlite. And furnace cool means that we put this is the cooling temperature, the cooling rate is very slow because it is in the furnace. So we can have this is coarse pearlite because it is and the cooling cooling rate is very low. And then we can have this normalized also for steel, and deformed steel with large grain. Normalized means this, deformed steel with large grains, and then heat treat and to allow this recrystallization and formation of smaller the grains. This normalization results in the smaller grains, and which also consequently results in a stronger material. Another one is process annealing. Negate the effects of cold working by recovery and recrystallization. So this slide shows different types of annealing and how to carry out these different types of annealing. So I hope you guys understand all of these different types of annealing. You do not need to memorize these, and you need to understand. Okay? So if I were you guys, I would like to know stress relief and spheroidizing, full annealing, normalizing, along with this process annealing. I know some basic ideas. If there is a need, I just come back to see this slide. And I know the fundamental principles of annealing. Elevate the temperature and stay there, soak and hold for a certain amount of time, and then cool down the specimens. So I know these things. And then we talk about this thermal. This is moderately rapid and slow cooling the curve superimposed on a continuous cooling transformation diagram for eutectoid iron carbon alloy. So here, so this is do you still recall this curve? So this is the begin curve, and so this is a completion curve, and this is the middle curve, and the middle curve did not show. So this is a pearlite. Next to this is a pearlite. This is austenite. And so here, and high temperature and high rapid cooling rate, and we can result in we can get this fine pearlite. If the slow cooling rate is applied, and we can get this coarse pearlite. And so this is M, this marstenite. This M start 50%, 90%. So this is a sign and denotes a transformation during cooling. Right? So during cooling, you can see is a transformation from austenite to pearlite, either coarse pearlite or this fine pearlite. Any questions regarding this slide? No question? And we move on to the spheroidizing. And so this is spheroidizing, as the name suggests, and we want to get spheroidites. And this is spheroidite, this microstructure. And we heat the alloy at a temperature just below the eutectoid for the line 1. Okay, line 1, I showed you line 1 there. In the previous figure, or at about 700 degrees C in the ferritic plus the cementized region of the phase diagram. If the precursor microstructure contains pearlite, spheroidizing times will ordinarily range between 15 to 25 hours. And heating to a temperature just above the eutectoid temperature, and then either cooling very slowly in the furnace or holding at a temperature just below the eutectoid temperature, and heating and cooling alternatively and within about positive negative 50 degrees C of the A. This is the A1 line of figure 11.10. So heat, cooling, alternating within about this one. So you can get a spheroidite microstructure. And so for full kneading, right? For full kneading. And so here you can see this is the cooling curve. And the cooling curve passes, this is this continuous, right? This is continuous, passes this start, the begin curve, completion curve, this is a continuous cooling transformation curves, and it goes down until we finally get this martensite. So quenching. So this is a full annealing. So this is a quenching. And as the name suggests, quenching means that the cooling rate is very, very high. And how high? It is so high that, so this cooling rate, this cooling curve on this diagram, and just does not intersect. And this is the transformation curve. And you can see go this way, and we will get martensite directly. So tempering. And so this is tempering, right? So this is annealing, tempering, quenching. So tempering means that for martensite, for this martensite, as I said, martensite itself is very, very brittle, very, very hard, and they cannot be used directly in industrial applications. However, we can do something to make it softer but still strong enough. And how to do that? We call tempering. And tempering means tempered the martensite. Okay, so you can see go this way, and we elevate the temperature, and then hold some time, and then goes down, and when we get this tempered martensite. Tempered martensite can be used directly in engineering applications. And then we talk about hardenability and steel. For steel, what is the hardenability? Hardenability is a measure of the ability to form martensite, martensitic structure. It means that if this material it is very, very easy to form this martensite, we call this hardenability is very, very high. And on the contrary, if another material and it's very, very difficult to get the martensite, we say this material, the second material is having a lower hardenability. So how to measure this hardenability? We use Jominy and quench test to measure the hardenability. So this name is very, very beautiful name, Jominy and quench. So here is a specimen, it's this specimen here, and heated to this is gamma phase field, and to heated to gamma phase field. Okay, so gamma austenite, the gamma phase field, and then we have this is a room temperature water, and room temperature water is sprayed on this interface, on this interface of this specimen, and then we can see, and then we will measure. Okay, we will measure from this end to this end, and we measure the Rockwell C hardness value along this line, or along this line. Do you understand, guys? And I also want to know if you have already taken the mechanical engineering course or not, or you are taking mechanical engineering course now this semester concurrently with this material science. If you have taken or are taking mechanical engineering lab, and you might have already done this hardness testing already. So hardness testing, we have a Rockwell tester, hardness tester downstairs of FDH, and you should know that. Okay, so this is Rockwell. Also, I have mentioned several times. And for regarding the hardness testing, we have 4 different hardness the testing skills, testing methods. One is Rockwell, and second one is Brinell. Okay? Brinell, I said, HB means Brinell, HR means Rockwell, and we have Nooper and Whisker. And Nooper and Whisker, these two guys, they are designed specifically for micro hardness testing, and for this is a bigger scale hardness testing. Mainly we use Rockwell testing, hardness testing, or this Brinell and hardness testing. And Rockwell hardness testing, and this guy has 3 skills, and skill A, skill B, skill C. So that's the reason we know HRC HRC means harness, Rockwell harness for the skill C. Right? And as I said, if you have already taken ME, mechanical engineering lab already, or you are taking this lab this semester concurrently with this material science, you might know what's the difference between skill C, skill A, and skill B. Now, let's come back to our the topic we are talking about now. So when we measure hardness testing, and then you can see we can just draw this figure. And so this is the distance from the quenched end. This is the quenched end, and definitely at this is the quenched end, the temperature, the cooling rate is high because so this surface, this face is touching the cold water. I'm sorry, not cold water, room temperature water. We still say it's cold water directly. So this guy has higher the cooling rate than the locations that along this is specimen longitudinally from this end to this end. So as a result, at this point, and it should have the highest HRC hardness. And it goes down as the distance from the quenched end increases. You can see it goes down this way. And any questions regarding this slide? And so because this slide is very important, I want you guys to know several important points I want you guys to pay attention to. First, what is the Jobney and quenching test? What is it? And what is it for? And second, what is Rockwell hardness testing? And also, how many hardness testing methods we have? I told you four hardness testing: Rockwell, Burnell, Vickers, and Knoop. This is for the different hardness testing skills. And what is hardenability? So this hardenability is a measurement, is a measure of the ability to form martensite, and it is easiness. It is whether it is the capability, okay, of capability of this material and to be quenched to get martensite. So reason and why hardness changes with distance. This I just mentioned briefly, but here is the cooling rate decreases with distance from quenched end. And just as I mentioned, because the quenched end, it is touching the water, the cooling medium directly. And so this guy has the lowest, the highest cooling rate. As a result, at this point, it is much easier to get the martensite. And so you can see this is the cooling rate. The hardness testing, we can go this hardness HRC and goes down very soon. You can this is longitudinal this distance from the point of interest to the quenched end. You can see it goes down very quickly. So here, so this is martensite. Okay, so this is martensite. So if we have this here is from austenite to the pearlite. If the cooling rate is high enough, so this cooling curve can avoid the nose of this starter curve, so it can go to get this martensite. You can see this point, for this point correspond to this point. You can this cooling rate is very high enough, and so it can avoid this the nose of this starter curve and to get this martensite. So this is second point. Second point is the cooling rate is a little bit low, a little bit faster than this one, lower than this one. So this curve intersects this is starter curve at this point, and so still get some martensite. So this guy martensite plus this pearlite. So as a result, this guy has higher hardness. This guy has lower hardness. So this one, for this temperature, for this is point, the cooling rate is much lower than this one. So we can get this. So this guy intersects. So these are both this starter curve and also this and the curve, completion curve, and go here, and we will get this fine pearlite. Fine pearlite is softer than martenite. So this point, right, for this point, and this point is the cooling rate is much slower, and it goes down and go here, and we get this is a pearlite, right? So this get a pearlite. And then we talk about the hardenability versus alloy composition and how the alloying elements affect the hardenability of the material. So you can see here hardenability curve for 5 alloys, each with and C equals 0.4 with percent of carbon. As you can see, distance from the quenched end. And so this is hardness HRC. And so here is a 1040, this is a 1040. Okay, this is a 5140, 6040, 4140. So this one. So this is the cooling rate. Okay, so this is the cooling rate. So here this is a 1040. So this is a 5140, 4140, and this is the 4340. So this is a cooling rate, distance from the quenched end. The cooling rate, we say, cooling rate this one at this end is much lower. So this is for alloy steels. 41, 4340, 5140, along with 6040. Okay, so they contain nickel, chromium, molybdenum, 0.2 to 2 with percent. And these elements shift the nodes to longer time from A to B and push this one from A to B. That means for this one, even the lower cooling rate, and for this curve B, at this lower slow cooling rate can still avoid the nodes of this is the new transformation curve. As a result, even this one I can still get martenite. So this is the these elements shift the nodes to longer time from A to B. So that means martenite is easier to form. So I hope you understand. And so this is the figure. Any questions about this slide? So let me recap what I just said for this one. Okay, and for if we have alloying elements in the steel, so these alloying elements tend to retard or push the begin curve, and this is a completion curve of the phase transformation. As a result, even for lower cooling rate, because of the existence of these alloying elements, for this new transformation, I can lower cooling rate can still avoid the nodes of the new phase transformation curve. As a result, even with this lower cooling rate, I can still get martenite. So this is the significance of the alloying elements. I know I hope you guys can explain this one either in the quiz or in the upcoming exam. So this is very important. And I might ask, what is the significance of ending the alloying elements in the plain steel in terms of hardenability? And you should be able to tell me ending alloying elements and can retard the phase transformation curves. As a result, even lower cooling rate, lower cooling rate can still avoid the nodes of the phase transformation, the curves, both the start curve and this end curve or completion curve. As a result, even with lower cooling rate, because of the existence of the alloying elements, I can still get martensite. So you need to know this, and you should be able to use your own words to explain the significance of these alloying elements. And then we talk about the influence of quenching medium and specimen quenching medium and this specimen geometry. Quenching medium, we usually use water, oil, and the air. Okay, so you can see the medium, and we have uh, air. Air. This air is this. We don't need to have extra medium oil. We need to have extra water. And severity of quenching. And severity of quenching means that on how quickly we can lower the temperature of the place at which we spray this medium on. So this is for air low, right? So this is the cooling rate is low. Oil is moderate. The water is very high. So as a result, hardness. If we use air, the hardness is low. Why? Because the cooling rate is low, and we cannot fully get this martensite. As a result, we can have martensite or perlite, or even we cannot get any this martensite. As a result, hardness is low. And the water is another extreme. So hardness is high because we can get when we use the water as a medium for the quenching test, and we have higher cooling rate. As a result, we can have more possible. This is more possible that we can get martensite, or we can get the combination of martensite and this perlite. As a result, we have higher hardness. For the oil, and the resultant hardness is located in between. So it is moderate. Questions regarding this one? And three medium materials, we have air, oil, water. So in fact, of the specimen geometry also makes a big difference. So when the surface area to volume ratio increases, the cooling rate throughout interior increases, and hardness throughout interior increases. So this is understandable, right? So if the surface area to the volume ratio increases, that means with this guy has more surface and to absorb, to release the heat, and as a result, and you can get more locations on this material will have higher cooling rate that is high enough to make sure we get this resultant martensite. Position, center, and surface. Cooling rate is low and high, right? It is understandable. And hardness is low and high. I mean, my surface is have higher cooling rate. Center has lower cooling rate. Any questions regarding this slide? No question? We move on to influence of quenching medium and specimen and geometry. This is the graphical representation. So here is the geometry. Okay, so this is the geometry. And so here is the 4140 and 1040. And so here, if which geometry is higher, 4140, and so this is 4140. Okay. So this is 4140. So but increase the temperature. You can see radial hardness profile. This is radial hardness profile. Okay, goes down. For A and B, a diameter cylindrical specimen of 45 steel quenched in mildly agitated oil. Any questions regarding this slide? No question? We move on to the precipitation hardening. And as I said, the precipitation hardening is one of the most important the hardening mechanisms for metal and metal alloys. And the other three hardening mechanisms include reducing the grain size and forming for solid solutions and cold working. So this is the first one. And so we can see appreciable maximum solubility of one component in the other, and precipitation. A solubility limit that rapidly decrease in concentration of the major components with the temperature reduction. So the composition of a precipitation hardenable alloy must be less than the maximum solubility. So this is a hypothetical phase diagram for a precipitation and hardenable alloy of composition CO here. So this is liquid, alpha plus liquid, beta plus liquid. So this is alpha, this is alpha plus beta, and this beta. Right? This is a precipitation hardening. The particles impede dislocation motion. And so this is the major reason that precipitation can harden the material. So I want you guys to know, right? So for example, this is a aluminum copper system. And so for this one, right? So this is a combination range available for precipitation hardening. So procedure. The solution heat treat and to get alpha solid solution. Part B. This is part B. Okay? The quench to room temperature to retain this alpha solid solution. And part C, reheat to nucleate small theta particles and within alpha phase. So this is the temperature on part A, solution and heat treat, and so this is part C, precipitate, and this is part B here. So this is the time. So other alloys that precipitation harden, for example, CuBe, CuSN, and Mg, magnesium, and aluminum. So basic precipitation hardening. This is a schematic diagram showing strength and hardness as a function of the logarithm of aging time at constant temperature and during the precipitation heat treatment. So here is the zones. Here is the overaging. So this is the theta is precipitation particles. So this is the precipitation hardening. Okay, so this is solid, solvent and solute, and solvent and solute. So this is theta. This is a theta particle, phase particle. This is theta phase particle. Influence of precipitation heat treatment on this tensile strength and also elongation percentage. Elongation percentage indicates the ductility of the material. For example, 2014 aluminum alloy, maximum on tensile stress curve increasing, and this is as a increasing tensile strength, increasing T accelerates the process. So this is the tensile strength. So this is the precipitation heat treated time, 1 minute to 1 year. You can see no equilibrium solid solution, many solid small precipitation aged and going down. And here is the fewer large precipitation overaged. So maximum of elongation percentage, the curves go this way and go this way.